In the next 3 lectures, we are going to see what happens to optical pulses when they propagate through an optical fiber. And in these 3 lectures, we will concentrate only on multimode fiber and see what happens to the pulses. So, I will start with this transmission characteristics of an optical fiber and part 1, and in this part I will concentrate on attenuation of signal. In order to understand attenuation of signal and do calculations, particular units dB and dBm units are very handy. So, we are going to look into these units. Then what are the loss mechanisms in fused silica glass fiber? At what wavelength you have the lowest loss? What are various communication bands? And what is a futuristic system we are looking at? So, these things we are going to do in this lecture. So, let us look at the propagation of optical pulses through an optical fiber. So, if I have my data encoded in a pulse train, your optical pulse train, a sequence of zeros and ones, and when I send this pulse train through an optical fiber, then at the output end the shape of the pulses become something like this. What I notice here is the amplitude of these pulses, the power level of these pulses, it goes down, and at the same time the duration of pulses increases. So, when I send these pulses through optical fiber and the pulses become like this, then I will have to pay attention, I will have to take care that these pulses do not overlap. Also, the power level of the pulses should remain at such a level that the optical detector should be able to detect them. Otherwise, I will lose information. So, before these pulses are overlapped or their power levels go down to beyond a certain limit, I will have to reshape the pulses. I will have to bring them to their original form, and this is done in a device known as repeater. So, in a communication link, you send pulses through optical fiber, and then after a certain distance you will have to reshape the pulses and bring them to their original form, and then you again send it to the next segment and then to the next segment and so on. If L is the repeaterless length of the link, then this repeaterless length of the link for a given data rate depends upon 2 things. One is how much the pulses have attenuated, and what is the spread of these pulses, what is the broadening in these pulses so that they do not overlap. So, we are going to look into these 2 things in next lectures, next few lectures. In this particular lecture, I will pay attention to the attenuation problem. So, what is attenuation? That the power at the input end which I send through an optical fiber, if it is P in, and the power that I receive at the output end is P out, then I define the loss of the link, loss of this fiber through length L as, in dB units, 10 times log at base 10 P in over P out. So, this is the loss in dB through L length of an optical fiber. It is often convenient to to represent this loss in terms of loss coefficient, which is loss in dB per kilometer length of the fiber. So, I divide this thing by L and I get this loss coefficient alpha in dB per kilometer units, where L is in kilometers. It would be nice to have a conversion from linear to dB units. So, if P in over P out is 1, then there is no loss, the loss is 0 dB. If it is a factor of 10, then it is 10 dB, a factor of 100 means 20 dB, and a factor of 1000 means it is 30 dB loss. To facilitate calculations, it is also convenient if I represent power also in terms of dB units, but dB units involve log, and I can take log of only a ratio. So, how would I represent power which is in milliwatt or power in watt into dB units? For that I take a reference. For example, if I take a reference of 1 milliwatt, so if I say that P0 reference is 1 milliwatt, then I can, whatever power I want to now represent in dBm, that I can take with reference to this. So, I take ratio of this P with my 1 milliwatt and then take its log at base 10 multiplied by 10, then it becomes power in dBm units. So, here it is the same, that if I want to represent power in dB units, so I can represent it as log of power when I represent power in milliwatt and then multiplied by 10, then it is dBm units. M stands for milliwatt, that is I am taking the reference as milliwatt. You can also have dVW units when the reference is 1 watt, and this is the conversion. If the power is 1 milliwatt, then it is basically 0 dBm, a 10 milliwatt of power is 10 dBm, 100 milliwatt power of is 20 dBm, and 1000 is 30 dBm, and so on. Similarly, if I go below 1 milliwatt, let us say I have 0.1 milliwatt power, then it is minus 10 dBm. So, in this way we will represent power, and using dB units and dBm units, the calculations become very easy. For example, I can now represent loss by simply this P in dBm units minus P out in dBm units. So, if I have a fiber in a link and the loss is 20 dB and I have the input power into the fiber 30 dBm, then the power at the output end would be simply 30 dBm, the input power, minus the loss 20 dB. So, it would be simply 10 dBm. But I should be very careful that I know that if there is multiplication or division in linear units, then it would correspond to addition or subtraction in dB units. However, if I have addition or subtraction in linear units, I cannot represent it in dB units. So, I should be careful while using this. Now, let us look at loss in glass, how the transmission in glass evolved over time. So, here I have plotted optical loss in dB per kilometer with time, which has been taken from IEEE Circuits Devices magazine 1989. So, if I look at it, you please look that on x axis it is not equally divided years, equally divided scales. So if I look at Egyptian age around 3000 BC, the loss in glass was something like 10 to the power 7, 10 to the power 7 dB per kilometer. When you come down to Venetian age, then the loss is about 10 to the power 5. The glass was almost opaque, you can't see through this. Then in 1900 around 1000 dB per kilometer, and if you look around late 60s or in mid 60s, the loss was around 100 dB per kilometer. That is where Charles Cow proposed that the loss should come down to 20 dB per kilometer for the fiber to be used in telecommunication. So it was that point. From here now you see the optical fiber came up, low loss optical fiber came up. This is the point representing 1970, the fiber produced by Corning Glass Work, which was having a loss of 16 dB per kilometer, and then you see a sharp fall. Okay, you see here it is 3000 BC, 1000 AD, and then 1900, 1966, and you see the time difference is much smaller here. From 1966 to 1979, within 13 years, you can see how much advancement has been done and how much the attenuation could be brought down in an optical fiber. And now we have a fiber which has a loss of 0.2 dB per kilometer. And if I look at the spectral loss variation in fused silica glass fiber, it looks like this. This is the spectral loss of 2.2 kilometer single mode fiber with core diameter of 9.4 micrometer and about 0.2% relative index difference. So if you look at this, then I see certain trends here. One is Rayleigh scattering. You can see that towards shorter wavelengths the loss increases, and if I see this trend carefully, then I will find out that it goes as 1 over lambda to the power 4. So it is Rayleigh scattering. Another trend that I see is infrared absorption. It is the tail of infrared absorption which extends into this region, and these two are water peaks. Now these two very high peaks are water peaks, OH ion absorption, and here I have the lowest loss at 0.2 dB per kilometer, which occurs at 1550 nanometer wavelength. Now what are the loss mechanisms in an optical fiber? What causes loss? So there are various mechanisms. I can divide them broadly into three. One is absorptive, another is radiative, and yet another is Fresnel reflection. In absorptive loss mechanisms, I divide it into two: intrinsic, which is the absorption by primary constituent materials of the fiber, and then extrinsic, which is the losses due to absorption by impurities. In radiative, it is primarily Rayleigh scattering, and then we have Fresnel reflection, which is caused by index contrast at the output end of the fiber. So let us first look at intrinsic loss. So it is IR absorption in SiO2. So, first I look at IR absorption at SiO2, which is this. So, what I can see is that as I go towards longer wavelength side, the IR absorption in silica glass increases. It has a peak beyond 2 micron. So, it is the tail of that peak which comes into this wavelength window. And this IR absorption is due to atomic vibration band in the near IR region, and it is the result of interaction between vibrating chemical bonds and electromagnetic fields. So, these electromagnetic fields give energy to these vibrating chemical bonds, and this causes attenuation in this wavelength range. I have marked here 3 wavelengths. At 1300 nanometer, it is very small, 4.6 into 10 to the power minus 5 dB per kilometer. At 1550, it is 0.018 dB per kilometer, and as I go towards 2 micron at 1800 nanometer wavelength, it becomes 1.3 dB per kilometer, and beyond that it even increases, it further increases. This is the snapshot of a software light sim which is available with Fiber Optica Technologies, Bangalore. Next is UV absorption by primary constituent materials of the fiber, which can be silica or germanium doped silica, and it is due to electronic absorption band in the UV region. So, it goes like this, and since the core is usually doped with germanium, so if I look at that, then I see that it increases with germanium concentration in the core. But this loss is much smaller if I go to infrared region. At 800 nanometer wavelength, the loss is 0.19 dB per kilometer, which decreases to 0.036 dB per kilometer as I extend into infrared region at 1100 nanometer. Then at 1300 nanometer, it is even down 0.018, and at 1550 just 0.01 dB per kilometer. So, I can see that if I look at 1550 nanometer wavelength, which is lowest loss wavelength for fused silica glass fiber, the contribution of UV absorption is negligible, it is just 0.01. And I had also seen that at 1550 the IR absorption loss contribution is also very small, 0.018. Next is the extrinsic losses in an optical fiber, which are caused by various impurities in the fiber. So, here in this table we are showing what are the losses and at what wavelengths they occur due to various impurities of, for example, iron, copper, chromium, vanadium and water. So, this is the loss in dB per kilometer due to 1 ppm of impurity, and these are the absorption peaks. For iron, I can see that for Fe2 plus it is as large as 0.68 dB per kilometer, which occurs at 1100 nanometer wavelength. For chromium, it is 1.6 dB per kilometer at 625 nanometer wavelength, and I see 2 very large water peaks here. Okay, out of 3, these 2 are very large. At 1240, 2 dB per kilometer, and at 1380 it is 4 dB per kilometer due to 1 ppm of impurity. But now tremendous advancement has taken place, and people have now got rid of most of the impurities and even the water. Okay. So, this is state of the art fiber from Corning Glass Works, which is low water peak fiber, and I can see here that it is very smooth attenuation curve and it does not have any peaks. Okay. And if I look at losses at various wavelengths, it is extremely small loss. So, you can see near 1380 nanometer wavelength where we had very large water peak, now it has loss of only 0.29 dB per kilometer. Okay. At 1550 it has a loss of 0.19 dB per kilometer. Apart from these absorptive loss mechanisms, we have radiative loss mechanism, and this is primarily due to Rayleigh scattering, and this is caused by wavelength scale inhomogeneities which are frozen in the fiber during the process of fabrication. So, you have scattering centers which are developed during the fabrication process, and when light hits any of these scattering centers, then it scatters light in all the directions. When it scatters light in all the directions, then only the rays here which make larger angle from the normal of core cladding interface, they are totally internally reflected and are guided, while all the other rays are refracted into the cladding and are lost, and this causes attenuation in the fiber, in the output power from the fiber. And this Rayleigh scattering loss in pure fused silica is given by this relationship which has been obtained by empirical fitting. Alpha at lambda is given by alpha 0 times lambda 0 over lambda to the power 4, where alpha 0 is 1.7 dB per kilometer and lambda 0 is 0.85 micrometer. So, if I know this formula, I can find out loss at any wavelength. So, this shows how Rayleigh scattering loss varies with wavelength, and I can see that as I decrease wavelength, the loss increases. Rayleigh scattering loss at 3 representative wavelengths. At 850 nanometer it is 1.9 dB per kilometer, at 1300 nanometer wavelength it is 0.35 dB per kilometer, and at 1550 it is 0.18. So, you can see at 1550 nanometer wavelength the Rayleigh scattering loss is 0.18 and total loss is around 0.2 dB per kilometer. So, major contribution to loss at 1550 nanometer wavelength comes from Rayleigh scattering. Let us take one example. If I have a laser diode at 1300 nanometer wavelength and I launch about 100 microwatt of power from this laser diode into a 10 kilometer long fused silica glass fiber, and if I know that the Rayleigh scattering loss coefficient of the fiber is 1.7 dB per kilometer at 850 nanometer wavelength, then what would be the power which would be exiting at the output end of the fiber? So, if I now calculate, of course, the calculation would be simpler if I use dB units. So, I convert this input power which is 100 microwatt into dBm units. So, Pn is minus 10 dBm, and now if I calculate Rayleigh scattering loss coefficient at 1300 nanometer wavelength, then it comes out to be 0.31 dB per kilometer. Since it is 10 kilometer long fiber, so the total Rayleigh scattering loss would be 3.1 dB and P out would be simply minus 10 dBm minus 3.1, which is minus 13.1 dBm. If you convert it into linear units, it will come out to be about 50 microwatt, and it is obvious, since the loss is 3 dB, then the power that will come out would be 50% of input power. Now, the next is Fresnel reflection. When light hits the output end of the fiber, then there is an index contrast. Here you have core with refractive index N1, and here you have air refractive index N0, which is 1 basically. And I know that for an axial ray, because of this index contrast, if I calculate the reflected power, then it is given by N1 minus N0 whole square divided by N1 plus N0 whole square. And if it is glass, so for glass, if I typically take N1 is equal to 1.5 and N0 for air is 1, then the reflected power is about 4%. So here I will have at least 4% power will be reflected, and here I will have more than 96% power which will go out of the fiber. These are various communication bands. Okay. Here I can see the attenuation curve and various communication bands. This is the first window, which is centered around 850 nanometer wavelength. This is the second window, which is centered at 1300 nanometer wavelength and has a loss of typically 0.5 dB per kilometer, and this is the third and latest window, which is used in long haul telecommunication, which is centered around 1550 nanometer wavelength and has a loss up to 0.3 dB per kilometer. And in this 1550 nanometer window itself, we have several bands. The conventional one, which is also known as C band, ranges from 1530 to 1565 nanometer. Then there is a short band ranging from 1460 to 1530 nanometer wavelength, long band from 1565 to 1625, and U band, which is ultra long, 1625 to 1675 nanometer wavelength. Then what is the futuristic system? Can we still bring down the loss of the optical fiber? In silica glass fiber, I have seen that the lowest loss wavelength is 1550, where the effect of Rayleigh scattering has almost diminished and the effect and the tail of infrared absorption has also almost died down. I know that if I increase the wavelength further, if I go towards longer wavelength, then I can still decrease Rayleigh scattering loss. For example, if I operate around 2 micrometer wavelength, the Rayleigh scattering loss can be brought down too much. But at the same time, if I use silica glass fiber, then infrared absorption is very high. Infrared absorption is very high at around 2 micrometer wavelength. So I cannot use silica glass fiber if I work at 2 micrometer wavelength. Then what to do? We will have to look for other materials where the infrared absorption is much smaller. And one option is fluoride glasses, where the infrared absorption peak is at around 50 micrometer wavelength and at 2 micron wavelength the loss is infrared absorption loss is 0.01 dB per kilometer. So, you see right now I have the loss of about 0.2 dB per kilometer. I can bring it down to 0.01 dB per kilometer if I use fluoride glasses, which means I can have repeater spacings more than 1000 kilometers, which is presently around 100 kilometer. However, there are problems that there are fabrication problems of the fiber. Then we need to have sources at 2 micrometer wavelength which we can use. We should have detectors at 2 micrometer wavelengths. So these reliable optical sources and detectors are still not available. So work is going on, but still they are not fully commercialized. So these are some issues with fluoride glass fiber system. So what are the points to remember in this lecture? We have seen that the optical pulses, they broaden and attenuate when they travel through an optical fiber. Then we looked into dB units which become very handy while dealing with losses in optical fibers, and 3 primary loss mechanisms in an optical fiber which has been kept straight. We have still not bent the fiber. These 3 mechanisms, primary mechanisms, are absorptive, radiative and Fresnel reflection. Absorptive losses are due to basic fiber materials, okay, it can be silica or germanium doped silica, and extrinsic are due to impurities. And in impurities, OH ion absorption results in high losses at around 1380 nanometer wavelength, but now there are no water peak fibers are commercially available. And we had also seen that wavelength scale inhomogeneities which are frozen during the fabrication process of an optical fiber cause scattering, and this is Rayleigh scattering loss, and this Rayleigh scattering loss varies as 1 over lambda to the power 4. Then a futuristic system has also been envisaged using fluoride glass fibers at 2 micrometer wavelength. Thank you.